Hello, everybody, ladies, gentlemen, and non-binary. Welcome back to our Würth Elektronik webinar. Today's webinar is actually Cable Ferrite Performance Assessment, partnered with Digi Key Electronics. Of course, Digi Key is the exclusive sponsor of all Würth Elektronik webinars. Digi Key Electronics is also located in Thief River Falls, Minnesota. If you ever get the chance to attend the Minnesota State Fair, I highly recommend it. I went there this last weekend and ate my body weight in fried foods. It was fantastic. So thank you, Minnesota, for hosting me this weekend. Back to our webinars. Today, again, Cable Ferrite Performance Assessment. Because you registered for today's webinar, you will automatically receive the video on demand when it becomes available. Might take us a few days, but we will be sending that to you through our email. It's webinarteam@we-online.com. Feel free to use the chat function, not the chat function, the questions function. If you would like to ask us questions throughout today's presentation, you can go ahead, test it out. Let me know if you've ever attended the state fair. And if you have, what is your favorite fried food? Because of course, we're American, and so we like that. But a lot of you are joining us from other countries as well. I see we have Australia tuning in. It's a little late for you, so I'm so happy that you are joining us for today's webinar. Now, if your questions don't get answered after today's presentation, or maybe you think of them a little bit later, you can always ask them at our email. It's webinarteam@we-online.com. We'll be responding back to you later on, hopefully immediately after today's webinar. Today's presenter is Stefan Schultz. He is a field application engineer with Würth Elektronik. Ooh, okay, we do have some questions, some topics coming in. Stefan, I might have to ask you what your favorite fried food is as well, because we have fried chicken coming in, and that is one of the best. So, Stefan, thank you for joining us for today's webinar. Again, if anybody has any questions, he'll be answering them after today's webinar. Don't forget to register for our next presentation on September 20th. It's Switch for Experts. It's how to choose a switch for your application. You can register online at www.we-online.com/webinar. Stefan, I will now hand it over to you as you present Cable Ferrite Performance Assessment, partnered with Digi Key Electronics.
Yes, thank you, Amelia, for the introduction. So welcome from my side also to our today's webinar with the title Cable Ferrite Performance Assessment. As my colleague already mentioned, I'm Stefan Schulz. I'm FA Key Account located in Germany. And yeah, I'm with Würth Elektronics for 11 years now. And those components that we will speak about today, yeah, since 2014-15, it's the main topic of my investigations offsite of Würth Elektronics. So I'm also working together with a university here in my hometown. And we made a lot of investigations, experiments, theoretical approaches. From one of them I will talk about today. And also some numerical simulations for cable ferrites. So what will be the content today, the agenda? After a short introduction to the topic, I will speak about and tell you about how those cable ferrite components are in principle characterized by nearly all manufacturers which you can find on the market. There's not a real standard for it, but it's kind of a process which everyone follows because it's quite simple. Then we go more into detail about the current distribution on a wire, on a cable, on a line, and in general, how it's possible to calculate this current distribution, and what impact a cable ferrite sleeve has on this current distribution. Then I will speak about how to increase the attenuation, just some general words about it, because in the first we will speak about only a solitary cable ferrite, but it's possible to extend the attenuation and to increase it by using different methods. And in the end, I will speak about an optimization process So how it's possible to achieve a wideband filter effect with more than one ferrite sleeve on a cable. And in the end, I will summarize everything. So let's introduce the topic. I think you all know those components, noise suppression components, the ferrite sleeves, which are mostly in the geometrical shapes of toroids or cylindrical geometries. And they can be solid ferrite, which are depicted here on the photograph, or there can be a snap-on ferrite, which is actually two ferrite halves clamped together with a plastic housing. And if the lock is closed, then also those two halves of the ferrite cores are touching each other without an air gap. So it's a fully magnetic circuit, and then we have the best performance if there's no air gap. Those components are mostly used in laboratories, in EMC laboratories, just to determine if a cable or any attached line, wire to a device carries a common mode current. So either during illumination from an electromagnetic field onto the device, that means immunity testing, or in the other way around, if it's emission testing, then also if there's a common mode current on the line, on the wire, then those components will be most effective. But of course, there are different factors which influence the performance of the cable ferrite. So the first is the frequency range of the noise. Different core materials are effective in different frequency ranges. So the material mixture also plays a big role in the selection of such components. But also the geometry, speaking about the length of the toroid, for example, or cylinder, and also the inner and outer diameter. So the inner diameter should always be suited to the outer diameter of the cable sheath. Then we have the best performance. But also the wire length determines how many standing waves or how many current maxima and minima are occurring at different frequencies and different wavelengths. So this is determined by the wire length, but also the wire layout, laying of the cable with respect to ground has an influence. And also the termination impedances on both sides, on both ends of the cable. And last but not least, the position of the cable ferrite along the cable also has a big impact on the performance. What we can state is that with a solitary cable ferrite at the fixed position, it's not possible to achieve a wideband filter effect. So at some frequencies and multiple of those frequencies we can achieve a good attenuation, but in between it can even lead to a gain or actually an amplification of the signal. Let's go a bit deeper into the theory of performance of cable ferrites on general transmission lines. So we know that the current distribution along the line, which is written here as a ICM, the common mode current, is depending on the frequency F and the position along the line X. And due to reflections at both ends of the cable and at the transition here between the cable and the ferrite sleeve, we find different reflections, different current distribution patterns along the wire at different frequencies. And what is also clear is that the radiated electromagnetic field is proportional to the magnitude of the current. That means if I can suppress a current, if I can reduce the magnitude of the current, I immediately also reduce the magnitude of the electric field, the magnetic field. So let's see how those components are normally characterized. It's a quite simple procedure, but it takes or it needs a quite expensive measurement equipment. Speaking, it's an impedance analyzer, or also a network analyzer would be possible to use but impedance analyzer takes into account and measures only the magnitude of the impedance. That is, in most cases, enough. We don't need phase information normally. So here's a picture of from our lab, and you see this impedance analyzer has a fixture which is normally used for SMD components, but we reuse it by attaching a small or short wire with a certain cross section. It's AWG26, which we take, and a certain length. So this length can differ for different part numbers. So in this example here, would be 165 millimeters length. This is a straight length of this wire. The wire is insulated and short-circuited on both ends here at the fixture. And the ferrite sleeve is then placed directly in the center, as best as possible to the center position of this cable. And then we can take, for example, one feed through, so feeding the wire only once through the sleeve. Then we name it, it's a one-turn configuration. Or if you wrap it around and feed it through a second time, then it's the two-turn or double-turn configuration and so on. You can add as many turns as you like, as long as the cable outer diameter allows it. So what we actually measure here with the impedance analyzer is a short-circuited wire loop and with a sleeve attached to it. And then we get results which look like this as an example. So here we see the inductive behavior of this component. There's an increasing frequency, increasing impedance, magnitude of the impedance in ohms, with rising frequency. Up to a certain point, which we find here, this is so-called self-resonance frequency. And it's not a sharp resonance, of course, but because we have losses in our component, and that's why we find here a wide band, a broadband peak, and quite flat hill. And the behavior which we see here above this resonance frequency, the first one, is due to this wire which we use for the measurement. So the longer the wire, the lower this point here in the frequency range. That's why we try to keep the wire length as short as possible, but allowing us to wrap around a second turn. So it must be long enough to wrap around a second turn to get a second diagram for the impedance. And those resonances here we find also in the transmission line theory. For every transmission line, there's always a mix of short circuit and open loop impedance. So the behavior here in the end, it's due to the mainly due to the wire, not due to the ferrite. So let's look at the current distribution in more detail. Therefore, I've selected an example, which we also measured in a semi-anechoic chamber, which you can see on the left side on this photograph. So it's a setup here on a wooden table. On the left side is a broadband noise generator, which goes up to 6 gigahertz. And there's this 1 meter long wire attached to it. And the wire is terminated by this metal box via a coaxial feed-through connector. And on the interior of the box, the wire is short-circuited, like is depicted here on this schematic. So actually what we have here is short circuit, and then this parasitic capacitance of the metal box with respect to the conducting floor. The distance here is 80 centimeters above the floor, length 1 meter. And for configuration 1, which is shown here, the ferrite sleeve was positioned at a distance of 10 centimeters away from the generator output port. We have, for the whole frequency range, a constant output power of 10 milliwatts, and the wire has an outer diameter of 1.5 millimeters. So both of those capacitances here for the generator side and the load side or termination side were calculated by a static approach using a 3D modeling software. And those are the values which you can see here. So there are some around 10 to 20 picofarads only. But those capacitances are important because they are part of the common mode current loop, which is formed here. And the return path is always a conducting floor. The equivalent transmission line model is shown here. So we have 3 sections. The first section is just a section before the ferrite sleeve, so between the generator and the ferrite, which is here in the center. And the third section is the part behind the ferrite sleeve. And the first and the third section consist only of the characteristic impedance of the line with respect to ground. So we need only an inductive per unit length parameter and a capacitive one. There are actually no losses. We can neglect the losses. Not so for the ferrite. The ferrite model is shown here. This is a full 4-port or quadrupole display of a standard ferrite model with 2 elements here, the combined inductance, per unit length inductance and per unit length capacitance. And those values are calculated by taking into account also the inductance between the wire and the ferrite sleeve and between the ferrite sleeve and the ground. The same for the capacitances. So all of them are connected in series. And the output voltage of the generator is also constant. For constant output power, we have 2 volts of voltage. So we have divided the 1 meter long cable into 1,000 sections. Each single section is 1 millimeter in length. So here we have some sections and then 46 sections here in the center and more than 800 in the end. In the investigated frequency range ranged from 1 megahertz up to 3 gigahertz. Here we see the used ferrite sleeve geometry. So the sleeve has an outer diameter of 12 millimeters, inner diameter of 6.1 millimeters, and an overall length of 46 millimeters. From that, we can derive a so-called geometry factor, K, which is related to the relation between the outer and the inner diameter. The material is nickel zinc, so it's a standard sintered ferrite material with a nickel oxide and zinc oxide content. And the initial permeability has a value of 620. Initial permittivity is only quite low, it's 25. But also the frequency-dependent behavior of the permeability and permittivity are taken into account. So also the dispersive effect is taken into account. So how can we calculate the per unit length ferrite parameters RL, G, and C? This is shown here with these quite simple equations. And here we find the imaginary and the real part of the permeability and the same for the permittivity, which are taken into account separately. And of course, the frequency also is hidden here inside the angular frequency omega. So we have, I've shown the schematic of the equivalent transmission line model, and this schematic we have translated into a SPICE netlist by using MATLAB. So it was automated process. So for each of the 600 frequencies, there was a frequency step of 5 megahertz. I have created a netlist, separate netlist, which was then afterwards simulated in LT-SPICE. So how is this netlist built? It consists of the parameter definitions in the beginning. Then we have the excitation here, just a single voltage source with an internal resistance of 50 ohms. Then we have the N1 LC segments for the first part of the transmission line. And the NFE, that's 46 segments for the ferrite, and N2 LC segments for the section behind the ferrite. After this definition, all inductor currents are saved. So for each single inductor in series, the current is saved automatically. And then we also have the simulation directive. I make a transient simulation, and after the transient simulation is finished, I perform the Fourier analysis. So taking only the magnitude of the first harmonic for each single inductance. So every millimeter I get a current value, which I then can display. And I want to show two examples for two different frequencies. The first one is one at 100 megahertz. So here's a comparison visible between the empty transmission line, that means without any ferrite, and the one with the configuration 1, that means 1 farad at 10 centimeter distance from the generator output port. So we are here in the milliamp range, so we have only 10 milliwatts of input power into the line, so we cannot expect to have amps or several hundreds of milliamps, so the current is quite low. But it doesn't matter because we want to see the effect of the attenuation. So attenuation is independent of the absolute value of the current. So here's this visible a slide, attenuation of the current, not that much, but still there's an effect. And for all positions along the line, the position here is on the x-axis, so from 0 to 1 meter. And of course, the frequency is relatively low compared to the length of the 1 meter wire. That's why we find only one maximum here of the current. At 1 gigahertz, so 10 times this frequency, of course, we have more than one current maximum and minimum. So here we find nearly 7 of the current maxima. And also we see clearly that there's an attenuation effect at every position along the line, except for the first 5-6 centimeters, where there is an amplification of the signal. But that doesn't matter because the main effect here is active. If most of the current is suppressed and attenuated along the line, then in general the far field electromagnetic field is also reduced. In the near field, of course, you can have some effects of increasing amplitude of the magnetic or electromagnetic field, but this is only at a very very small distance away from the line. So how it's possible, in principle, possible to increase the attenuation? So the first thing which you can do is choose a longer cable ferrite. So if we have a certain sleeve tested and the attenuation is not sufficient enough, then it's a good idea to choose a longer ferrite. So in this example here, we have the same outer and inner diameter, but the length is nearly double the one which we have used before. And length is always important. So the longer the cable ferrite sleeve, the higher the attenuation. And of course, the same we can achieve if we put more single shorter sleeves in series on the line. Then the impedance will increase linearly. So with a number of farad as a multiple. So if you take 2 farads, then the impedance should increase by a factor of 2. If it's the same type, the same geometry, the same material. But the strongest effect we can get if we have more than one turn. So if we wind the cable 2 turns or 2 times or 3 times through the opening of the farad, then we have the stronger effect because the impedance increasing is then proportional to the square of the number of turns. So for 2 turns, we should expect the impedance to increase by a factor of 4, and for 3 turns should be a factor of 9. And this can also be displayed here with a real measurement. So what I have done here is taking the original impedance curve, which I have shown already before, for a single farad as a reference. And the dashed curves here is actually the blue dashed curve here and the green dashed curve here on the top. These are all only shifted upwards by this factor of 2 for the blue curve and factor of 4 for the green curve. These are the theoretical results which I would expect if I take the mathematics into account only. But if we look at the real measurement, it's the solid lines here, green and blue, they already decrease here, and the maximum of the impedance is shifted towards lower frequencies. So because due to the additional wire turns, which I wind around the core, I increase the global inductance, and that's why the self-resonance frequency, the self-resonance point of the whole structure, including the short wire, is then increased, and this will lower the self-resonance frequency. And this is the same behavior for all materials, be it amorphous, nanocrystalline, manganese zinc, nickel zinc, magnesium zinc. So all materials have the same behavior. So let's look at the optimization. Is it possible to optimize the performance of ferrite sleeves along a line to reach a broadband effect? So we know that if I'm able to place a ferrite at the position of the current maximum for certain wavelengths, then it is placed optimally. But of course, we know that usually we don't have a single noise frequency, and which we need to suppress. So mostly we have frequency, base frequency, and the multiples, high harmonics, or even the broadband noise spectrum, which you need to attenuate. So by using only a solitary ferrite sleeve, it's not possible to reach this goal to have a wideband suppression. So what we can do? So take more than one ferrite sleeve. How many? That's a question. Still a question, yeah. But let's say we take 3 ferrite sleeves, identical ones, the same geometry, same material. And then we select the positions of those sleeves in a way that preferably many sections of distinct lengths are created. As many sections as possible of distinct lengths. And this is this principle of the so-called Coulomb ruler. The Coulomb ruler has a property that every set of marks at integer positions along the line or along the ruler is in such a way that no 2 pairs of marks are the same distance apart. So let's look at 2 examples for the so-called optimal Coulomb ruler of order 5 and length 11. So for the first example here, we see that if I choose the integer positions 1, 4, 9, and of course terminate by on the left and right side by 0 and 11, because it's length 11, then we find all distances except 6. So this is not a perfect Coulomb ruler, but it's an optimal one for the length 11. And the second example for the same length, these 2 are the principal solutions for the Coulomb ruler of length 11. So we find all distances except 10. Also an optimal Coulomb ruler. So I have translated this approach to our real setup. So here we show again the configuration 1, which was already investigated before. And the configuration 2 now shows the first Coulomb ruler configuration here. So as we simply placed the 3 ferrite sleeves at 10, 40, and 90 centimeters away from the generator port. And the second configuration is shown here, so 10, 70, and 80 centimeters away from the port. This should also give a similar result, or nearly the same result as a configuration before, configuration 2. And then configuration 4, shown here on the right side. This is the so-called best case, but it's not practical because no one wants to attach hundreds of sleeves along the 2 or 5 or 10 meter long cable, depending on what length you have, because it would be too heavy. It's not possible to handle this cable anymore. It's of course a quite expensive solution. But of course, from a suppression perspective, that would be the best case. So then at all frequencies, the current will be suppressed and decreased. So this is just for comparison, this configuration. It's what was not investigated by measurement before. So let's look at the results in comparison. Again, the reference is shown in black always, black color, the empty transmission line, and then the 3 configurations, excluding configuration 3, which gives nearly similar result compared to configuration 2. And at first one result is for 100 megahertz again, which we have seen already before. And you can see clearly that for all distances, there's a nearly equalized current magnitude. So this, and the distance here, attenuation at the current maximum is more than 20 dB, or even more than 30 dB. And just for comparison, the orange line here shows the best case configuration for this exponential decay of the current amplitude. And the same principle result we find for higher frequencies too. So for 500 megahertz, it's similar. There's always an attenuation, except for those distances here where we had some current minima before. So actually it's nearly zero, the current, but it's only the theoretical model. But in practice, we have a minimum current here, which is not exceeded. And only for a small distance here in the front, we find some amplification of the signal. But the overall view is clearly visible that it's the current is attenuated. And this goes on for higher frequencies. It's nearly similar, except that for 1 gigahertz at this specific frequency, we have an amplification of the signal here in the front of the line. But again, very good attenuation for all points along the line. And also for 3 gigahertz, it's the highest frequency which was investigated. There we find for all distances along the line very good and high attenuation of more than 40 decibels. And this is not the limit, so we can still go higher in frequency up to 5, 6, 10 gigahertz, and we would find a similar result. So the higher the frequencies, the stronger the attenuation. And this is not clearly visible if you look only on the impedance graph in the datasheet. So this is one result which we got from our investigations, that actually the attenuation is not really limited by frequency, because we still have these eddy current losses, and eddy current losses inside the ferrite are proportionate to the frequency. So, and the last result which I want to show is a more 3-dimensional view on the results. So here we have before we have seen only single frequencies, selected frequencies, but here I have displayed the attenuation factor for the current, which is calculated in this way, like shown here. So for all frequencies up to 3 gigahertz, and for all distances, attenuation is here depicted in decibel with different colors. So green color means neither attenuation nor amplification, and red and dark red colors are positive decibel, that means attenuation. Blue colors are amplification values. So this is a nice pattern which is visible here. So the red lines are 150 megahertz apart, which is clearly the frequency for half of the wavelength. So if we consider the whole 1 meter long cable as a half wavelength dipole, then we find the corresponding frequency at 150 megahertz. This is also a validation of the theoretical model. So the same is visible for configuration 2, that means our optimal Golomb ruler configuration. And of course, we have wider frequency ranges where we find positive decibels, that means positive attenuation of the noise signal, and in between some narrowband positions and frequency ranges where there's a slight amplification. And just for comparison, last but not least, the best case configuration 4. Of course, here it's actually cut it. At 60 dB, we find here even higher values up to 80 or 85 decibel attenuation in the end of the wire. So of course, this would give the best result. So let's summarize everything. So I've hopefully shown you that the impedance chart, which we find normally in a datasheet of cable ferrites, gives actually no real information about the actual attenuation and actual performance of a cable ferrite. It can be used for comparison, different part numbers among each other, but you don't have a real inside view how this component performs, especially for frequencies above the self-resonant frequency in the impedance chart. And I've shown you that attenuation, the real actual attenuation, depends on different parameters like the wire diameter, the wire impedance with respect to ground, the sleeve's position, and the ferrite material, and the sleeve geometry also, of course. For simple transmission line structures, it's possible to calculate the performance numerically, either by using SPICE or using MATLAB or other mathematical code. And in order to get a wide band filter effect, we need more than one ferrite sleeve and place them at positions given by the approach of the Coulomb ruler, optimal Coulomb ruler of a certain length and order. So that's all from my side, and now I'm awaiting your questions.
Thank you very much, Stefan. We do have a few questions rolling in here. And again, if you have any questions, feel free to ask them in the questions tab at the top of your screen. If you are not seeing your GoToWebinar questions box, just make sure that you have all of your settings signed up for that. We're going to go ahead and take a look at a few of our questions rolling in. We do have quite a few. So, I'm sorry, what?
Yeah. Should I mark them or not?
You certainly can.
We'll go just from the top.
Sure. Our first question here is there a physical limit for the performance of cable ferrites at higher frequencies?
Yeah, I think I've mentioned this just before, that there's actually no real physical limit, although the permeability and permittivity of ferrite materials decreases with frequency. So there's this dispersive effect due to the eddy currents, which are frequency proportional increasing. We always have a stronger attenuation effect and stronger losses, higher losses at higher frequencies. So it's actually not limited. Except we go to frequency ranges in the tens of gigahertz range, then we have also a difference effect, because when we are at wavelengths of the crystal structure of the for example the atom length or crystal length of the edges, then there are different effects. But it's normally not that the frequency range which we deal with normally, at least not yet, maybe later in the future. So there's still some potential for future applications and future improvements.
Excellent, thank you. Our next question that we have coming in, is it possible to determine the radiated field from the current distribution along the wire?
Yes, that would be in principle possible to calculate. It's quite a challenging approach. It needs a lot of mathematical background knowledge, but in principle it's possible. Yeah, numerically it's also the same. Like there are similar software programs available on the market, some commercial, some free of charge. And with that, if you have the current distribution for different positions along the line, it's possible to calculate it or let it calculate automatically by the method of moments, for example. Nobody will do it by hand, I assume, but yeah, it's possible.
Excellent, thank you. Another question that has rolled in here, how can I compare the parameters of ferrite sleeves from different manufacturers?
Yeah, that's not so easy to do because it depends, as I have hopefully showed, that it depends on the wire length which was used for the calibration of the component. So if it's not given in the datasheet what wire was used, cross section and the length especially, then actually you don't have a chance of finding and really comparing the components. You can only compare the geometry and maybe the ferrite material, which is sometimes also given, at least the permeability you find in some tables, for example. But the real comparison only can be done by measurement, by direct comparison.
Absolutely, and from my understanding, finding the ferrite material is next to impossible with a lot of manufacturers. Our next question that's come in your slide showing the increased attenuation with a longer ferrite and multiple turns, can you please explain again why the self-resonance frequency shifted lower?
Yeah. Is my screen still visible? I think yes. Yeah.
Yes, it is.
Maybe I should close. Yeah. The window undock. Yeah, this effect of decreasing the maximum point here of the impedance is the effect of increasing overall inductance. So because we wind around different or more than one turn around the core, this is then we create a small coil of the wire around the core, and this coil of course has its own inductance, and also the distance between the wire ends and between the different turns will affect the parasitic capacitance in the same way or similar way. Like the inductance is increased, so both effects combined, increasing inductance and increasing parasitic capacitance, lead to effect that the resonance point is shifted towards lower frequencies.
Thank you for your explanation. We have time for a few more questions here. Our next one, does temperature affect ferrite performance, frequency shift, or attenuation?
Both. So the temperature, actually the core material permeability is temperature dependent, but I would say in a positive way if you don't increase the temperature too much. That's why we also give for ferrite sleeves an upper temperature limit. For operating temperature limit, it's usually 105 or sometimes 85 degrees Celsius. 125 is a normal value because you have to stay below the so-called Curie temperature. If you would increase the Curie temperature, exceed it, then the permeability is lost completely. So it drops to 1 as a relative factor, and then you have only the effect of actually nothing. So it's an inductance of nearly 0 henries then. So you have to take into account. But if you stay inside the operating temperature range of a ferrite sleeve, then normally for higher temperatures, there's an increasing effect of the performance because the permeability rises with rising temperature. But yeah, normally you don't reach the Curie temperature. For some materials it's at 180 degrees. Most of the variety of mixtures goes beyond 200 degrees Celsius.
Thank you very much. Our next question, if adding a single ferrite to attenuate a specific frequency, does placement location along the cable affect attenuation? For example, are there nodes to be concerned about?
Let me understand it correctly. Yeah, actually, it's more try and error, because in advance you don't have information about the actual current maximum along a line if you have a real application in the EMC lab. So that's more than of try and error, shifting the ferrite along the cable and repeating the measurement, because you will not find right from the beginning the optimum position if you want to use only one or can only use one sleeve. So, but I would say 95% of the cases, which from my experience in the lab, it helped placing the ferrite sleeve, as near as possible to the noise source side. So maximum 10 centimeters away. So from nearly all cases that helped already. If the core material was chosen properly and the length was chosen properly and the diameter was chosen properly, then you already get a good result. If it's not enough, if you need some more decibel of attenuation to go below the limit line, then you need to perform some investigations, some shifting of the sleeve and repeating the measurement.
We'll get to a couple more questions here. And again, if your question does not get answered, we will make sure that we answer them after our presentation. We have a question here. Do you have any data showing the differences between the split ferrite and the solid ferrites?
In principle, that could be done using our red expert. So maybe I can show it. It's not inside the presentation, but it's possible to use our red expert tool for direct comparison of the different part numbers which we have, or different series. So maybe you know already this has a new view, so maybe you still know the old view, but here now the modules are in a different pattern, different layout. So here, if you know the series, it's a bit difficult to know in advance what's behind the names of StarTech and AFB and TUF, for example. But there should be, here's assembly technology. So there's decrease it. So assembly technology, you can select a filter here, for example, snap-on and solid, just to reduce the number of shown elements. And then, of course, you need to compare ferrite sleeves and snap-on ferrites which have a similar length. That's the main criteria. So the length is here. It's possible to sort this column, ascending or descending, as we like. So let's see if we find a similar, or the star series which have plastic housing around the core. Yeah, it's difficult to find an example now because there are still not all elements visible. Just let's check an example here of StarTech compared to this AINA. So there should be a similar length available for both series. Yeah, for example, that one could be in principle compared with the solid series, which is AENA, and the StarTech is a snap-on, the clamp-on ferrite, which have a similar length, or around 30 millimeters. And is it also the same material? Not quite. Yeah, okay, the nanocrystalline material here is a bit different. So maybe I should select components which have a same material, which is nickel zinc in this case. So let's delete this one again and see if we find a similar component which has a similar length, but yeah, that one. So that would be the direct comparison of snap-on ferrite with a solid ferrite of nearly the same length, so 29 to 32 millimeters in length. Of course, they have different inner diameters, but I said the impedance is mainly affected by the length of the cable ferrite. So what you can see here is nearly equal curves, nearly on top of each other. So this would be a direct comparison.
Excellent, thank you. And Red Expert is a free tool that Würth Electronic does offer. You don't have to create a login, but if you do, you get so many more benefits, including free samples or free sample requests. So I highly recommend checking out Red Expert at www.we-online.com/redexpert. And I'll make sure that I include that link in the follow-up email as well. So we have time for one more question here. Very similar to the last one here. What's the difference between a ferrite clamp or a solid ferrite cylinder?
Yeah, I think that should be clear that the snap-on ferrite is, there are two halves, like the StarTech here. So we have two ferrite core halves which are equal in geometry and size, but they are sitting inside a plastic housing which can be closed. It has a lock and can be opened again using a special key from our side, the star key. And a solid ferrite just simply has no air gap. It's not possible to split it, so you have to feed it or have to feed the cable through before attaching and connecting the connectors in the end of the cable. So the big advantage of a snap-on ferrite is you can already have an assembled cable or cable harness with all connectors on the ends, at the ends. So it's very simple to attach it somewhere along the cable, and it's possible to remove it afterwards. Maybe after testing, if it's not sufficient, then you need to choose another one, another part number. Then it's quite easy to reattach it and to remove it and attach another one. From an electrical perspective, they are similar, like I have shown before.
Thank you very much. That concludes today's webinar and question and answer session. Again, if your questions did not get answered today, simply reply back to our follow-up email at webinarteam@we-online.com. And all of the questions that have come in here today, we will make sure that we reply to you directly. Simply check your email. So thank you, Stefan, for presenting today's Würth Electronic webinar. And thank you, everybody, for joining us. Again, you're going to be receiving the video on demand when it becomes available within the next few days. And if you want to know about any upcoming webinars or any news from Würth Electronic, you can follow Würth Electronic or myself, Amelia Thompson, on LinkedIn, and we will make sure that we get you all upcoming news from Würth Electronic. Don't forget to listen to the new Würth Electronic What's Up Radio podcast, where each week we are bringing application notes, blogs, press releases, and our webinars to an audio format. That again is the Würth Electronic What's Up podcast. This week's episode is Lifetime of Optocouplers. That goes live at Thursday, 12 p.m. Central. You can find the podcast on iTunes, Google Podcasts, Spotify, and all major podcast streaming networks. Again, don't forget to register for our next webinar coming up September 20th. As we present switches for experts, how to choose a switch for your application. As a reminder, this is an expert course, so you should have basic knowledge of switches already nailed down. You can register online at www.we-online.com/webinars. I'm Amelia Thompson. Thank you for joining us, and I hope to see you soon.
Yes, or wish you all a nice day or evening, depending on your location. And see you next time.